Okay, everyone. Hello and welcome again to the next lesson. Okay, now we are still in the queuing theory. Okay, it seems like this queuing theory is quite a lot. But now is the final part. Okay, part three. Unfortunately, okay, if you notice on part two, my video is a little bit cut off in the end. Okay, but by the end of the day, my teaser is actually is on the concept of instead of we replacing Mr. Blank heads on with that dashingly new mechanic. All right. What if we not change Mr. Blank, but instead we put additional mechanic similar expertise with Mr. Blank, not that expensive like the dashing Mr. X. Okay, we still pay this particular mechanic $15 per hour, meaning that the expertise is not that much. Okay, just similar level with Mr. Blank. How does the system change? Okay, so that is the teaser that you feel like suddenly it's being cut off. Okay, unfortunately, I am so sorry for that. Okay, so now since the teaser is already done, now we can proceed more to the queuing theory part 3. Okay, so what is this? Okay, what is this? We are now talking about the small m model. Again, it comes back to the candle notation. Okay, so if you notice, the difference between this and the previous version is just on your final m. Okay, the small caps m. Okay, this m representing your channel. Okay, now we are talking not necessarily on one channel only, but we are more at ease in finding different channel that we have. Okay, instead of just one counter, we have two, three different counters. M counters, but by the end of the day, your M should have limiting numbers, all right? Because we cannot calculate numbers that are not limited, right? Okay, so that makes sense. Okay, so now let's proceed. Okay, since we are talking about the same Markovian process, by right, we can jive them together the similar characteristic, the similar assumption as in your previous MM1 model. Isn't it? Okay, makes sense, right? Because you are dealing with a Markovian process in your arrival. You are also dealing with a Markovian process for your service time. So by right, it makes sense, right? The changes is only on your channels. Mm. So the whole these seven assumptions made quite similarly exactly as is on your previous MM1 model. Okay, so I don't need to uh, re, uh, re-emphasize on the notations. All right. Okay. So now let's proceed. Okay. We still have the same lambda as your average arrival rate, which you need to find. And then we still need mu, which is your average service rate. Also, you need to find. Okay. But this one, your mu is the average service rate at each channel. Okay. And then your M now is the number of channels open. Okay, so meaning that in that case, if let's say earlier you have one, for example, you want to proceed to ATM machine. Now you have four ATM machines, and then you have long line, and then your ATM machine now is becoming a little bit more efficient, isn't it? You don't have to wait that long to be served. Okay, so that is the concept of having different channels put together. Okay, so if you notice, we still have these seven different operating characteristic similar. Okay, but the difference now is on the formulation behind the valuation. Okay, previously your MM1, you feels like your formulation is straightforward, isn't it? You have lambda, you have mu, but now, for example, your peanut. Okay, your peanut is a little bit extensive. You can see over here we have a little bit of factorial valuation. Okay, we have um, n, we have lambda, we have mu, and we have sigma, the summation of all these things. Okay. Okay. Okay, I need to emphasize a little bit on the formulation, all right? Okay, if you notice, the Poisson process is okay. I'm so sorry, but I need to touch a little bit on your previous understanding, okay, on your statistical formulation and things like that. Even if you are if let's say you forget about them already, go back and listen, go back and harness yourself a little bit on your previous knowledge, okay, because I know you understand this thing if you learn, if you read a little bit, okay. It's not that just okay, I have this formulation and I carbon copy this into my brain. It does not work that way, okay. If you notice, okay, why we have this factorial, right? Okay, unfortunately I need to say a little bit on this, okay. If you see why we have this factorial and why we have this kind of valuation and this kind of sigma, if you go back to your Poisson process, okay, you can see if you read back, okay, on your previous lesson, statistic, early introduction on your statistical probabilistic, uh, Poisson process is quite similar. Okay, it's just an extension to your binomial process. All right, and then you have to remember back. Oh, what is binomial process? Binomial process is a process where you have a situation. Um, if then something like that. You have a situation where you have it's like how to say it. It's a binomial process. Okay, meaning that um it's like before, after, the continuation of that is what, and if you study a little bit, you can see when you do the binomial distribution, it does not shy away with a factorial valuation. Okay. So it must have some similar interaction between this formulation, right? Based from your Poisson binomial and so on, because Poisson is just a little bit extension on your binomial theory. Okay, so if let's say you have a little bit more time to dwell on it, okay, I would recommend you to try and find the way how we are able to construct this formulation from scratch. Okay, but by the end of the day, I would recommend you to start it based from the previous example MM1, and then later you can improvise into MMM. It's a little bit need a little bit more work, but it's worth it. Okay, so I leave that with you for you to figure out how to do these things. All right. Okay. In our case right now, in our mathematical model focus right now, we just want to know how are we able to get our P naught, P lambda, and so on. Okay, so P lambda, okay, Pn greater than K, and so on. Okay, so how to do just that? We use this particular formulation. It's a little bit tricky compared to the previous MM1 model, but you have to remember, if let's say we are using this solving this by using a software, it now becomes easy, isn't it? All right, but you need to know, okay, this is the formulation. Okay, but if you need to calculate it by hand, if you want to calculate it by hand, please do not forget to include this. The summation valuation is a very, very important criteria. Normally, people forgot about this summation and they just calculate it as is. It does not matter. Okay, so that is something that you need to be very, very careful when you start to look at your MM1. Oh, sorry, your MMM process. Okay, so the same thing happens for your L, W, and so on. Okay, but you can see over here, you now start with different kind of alternative. You have your factorial valuation and so on. Okay, but by the end of the day, if you notice, you still have seven characteristic. you still have your L and your LQ, you still have your W and your WQ, you still have your rho, and then you still have your P naught, and you still have your P and greater than K. All right, so that's how it yeah, how, that's how it goes. Okay, now we revisit about the muffler process. Okay, as I mentioned in the teaser previously, this Arnold guy, whatever happened if let's say he wants to open a new bay, okay, a new bay, a new second garage, a second garage bay. Opening a new bay meaning that you need to hire a new guy. All right, a new guy. Okay, so now Arnold want to hire a guy, a second worker, with the same expertise with Mr. Blank. Okay. Now what happened? Okay. Now we do all the calculation all over again. But right now your calculation now should include your new M. Your new M now is equals to 2. Okay. So now your P naught must be equipped with this different M, and so on. Even though you can see the changes of M from 1 to 2 only, but then you now start to look at the different summation for your this one. For example, instead of previously, there is no such thing as sigma, isn't it? For P naught, your P naught is just like your lambda over mu, I think, if I'm not mistaken, and then you have a little bit of subscript, the power over this particular lambda over mu. But right now, it is no way you do it like that, right? So you need to do the difficult part. Okay, you need to calculate slowly one by one, and by right, this is the probability now that you have. Okay. So I think you can calculate this on your own. Okay, the same thing happens. You calculate L, W, LQ, WQ, WQ, and rho, and what you get is all the 0.7. Your L is 0.75, and so on, so on, so on. What I am more interested in, okay, this one you can calculate. Okay, now what's what I'm more interested in is on your total cost, because that is our main intention, right? Okay, if we want to open a new bay, we want to see is there any significant difference between the previous decision that we made with this one. Okay, and if let's say we have three different opportunity for us to proceed, okay, whether to just maintain your status quo, or whether you want to lay off everyone, lay off Mr. Blank and find another more expert and productive person, or whether we don't need to lay off Mr. Blank, we keep him as he is. We are very satisfied with his performance even though underperform. But we don't go for this dashingly Mr. X, but we install or we hire another person similar to Mr. Blank. Which one is more economical, which one is more productive to you? Okay, because you are the owner of the shop. Okay, so it is your money. Okay, it is not Mr. Blank, Mr. Dashing X money. It's your money. So you need to really, really scrutinize your business decision, right? Okay, so how you do about that? Okay, so now you notice over here your total daily waiting cost, your total daily service cost, the calculation is just the same, right? It does not changes much, because it's not like the fundamental valuation depending on your lambda and your mu as in your previous operating characteristic. But it actually already embedded into your calculation for your operating characteristic. What does it mean by that? Okay, meaning that even though it looks quite similar like this, you can see there's no other difference between this. Okay, but you can see if you calculate your WQ now is different already, right? Because your WQ now is more comprehensively dependent on your M and so on. All right, so basically that is the changes over here. Okay, so how to go about this? Okay, you do the calculation, use your previous information from your previous operating characteristic and put that inside your main calculation over here. Okay, so once you do the calculation, you can see your waiting cost now becomes 33.20, and then your total daily service cost now, okay, is 240 because you are now considering two channel here. Okay, you are considering two Mr. Blank similar trait. Okay, so Mr. Blank 1 and Mr. Blank 2. Okay, so in this case, you once already put your two stuff over here, and then your total cost now becomes the summation of both service cost and also waiting cost. Now you have 270 point 20. All right, so if you get tired to go back to your original part 2 video, okay, I put over here. Okay, this is our initial cost when you have only Mr. Blank in place. You are left with 653, and then if you have a better mechanic, Mr. X, okay, your valuation now becomes 293.33. Whereas if let's say you want to hire, okay, Mr. Blank opposite, okay, you hire another Mr. Blank. Okay, so your cost now becomes 273.20. Based from these different alternative, you can see over here, this is your better alternatives. Okay, so better in the sense of minimum option. The cheapest option. Okay, so by the end of the day, actually Arnold should hire another one, but not that expert, because you can reduce the money spent for this particular guy. Okay, and at the same time, you can reduce a lot on the waiting time. So it's a win-win situation. All right. So this is how we solve certain alternative. If we have certain alternatives, okay, how best for us to solve this alternative, this is how we go about. Okay, so by the end of the day, these are the difference level. Okay, these are the difference level for your operating characteristic once you put that in action. Okay, alternative 1 with one mechanic, Mr. Blank, alternative 2 with two mechanics, and alternative 3 with one fast mechanic. Okay, so you can see the mu is the same for two earlier column, and then the final column mu is different, and you can see the difference in performance of these all operating characteristic is different. Okay, if you notice, the most significant difference is the average time spent in the system, the waiting time. Okay, the waiting time. If you notice, if you only have one mechanic, Mr. Blank, your waiting time is 60 minutes, which is quite a lot for a waiting time in a line. Okay, in a line, plus after service, meaning that the whole system is 60 minutes. It's a lot. Okay, and then your average time spent in queue is 40 minutes, meaning that uh, your your muffler is being installed for 20 minutes, so the 40 minutes time for you just to spend for you to only wait. Okay, interesting, isn't it? But if let's say you have two mechanic, you only need to wait in the line for 2.5 minutes. You come into the system, you wait for 2.5 minutes, and then another 20 minutes, your car is already is being installed with the new muffler. Interesting, right? Okay. But if let's say you have one fast mechanic, you need to wait for another 15 minutes in the line. Okay. Uh, 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 it's like that. Okay. And then another 15 minutes is for the muffler to be installed. Okay, because the mechanic is a little bit fast. Instead of 20 minutes for you to be for your car to be installed a muffler, now it reduced into 15 minutes. All right, and then your average number of cars in the queue is now significantly reduced. For example, one mechanic 1.33 cars, and then two mechanic, you see how different it changes, right? From one cars into less than one, not even less, but less than one fast mechanic even. Okay, you can see how it progresses that much. Okay, so these are the way we solve the same problem by using software. Okay, if you notice, that's why I said, if let's say you don't care much about the formulation, you just want to make it work. Okay, so you don't care about the statistical behind that. But again, as a quantitative people, okay, if you are concerned on your mathematical skills, okay, I would really really recommend you to revisit, okay, how you go about to construct your own formulation for the rest of your valuation on your operating characteristic. Because that one, it will give you more emphasis on how you can get to the particular value that you get. Okay, that's different, right? That's different. Okay, so if let's say you don't care about that, and you just want the output, okay, a fast, quick and easy output, okay, so these are the things that you need to input inside your software. Okay, your arrival rate, your service rate, and then the number of server. Difference is the number of server. And then once you click, oh, okay, I already put this one. This is the one when you have this one when you click the start running, and then this is the valuation that you have. All right, and then as usual, you can get all your additional figure and illustrations for you to get a hang of it. Okay, and these are the different case, okay, and with different probability, p n greater than k. All right, and these are of course software. It always give you more than you ask for, okay, but by the end of the day, these are the answer that you need. All right, okay, so I think that's about it for our queuing theory. um just an additional information for you to consider. Okay, as I said, we are only touch on the very very basic system, basic but very beneficial, because there are lots of system you can calculate by using this particular basis. Okay, but if let's say you want to know more, there are lots of other queuing model. Okay, we have MD1, MM1 with finite source, MM1, MMM with with finite source, and so on. Okay, so if you notice D over here, okay, D over here, meaning that this one is the Markovian, right? Okay, but D is another distribution, different kind of distribution. For example, that you need to consider uniform, I think, if I'm not mistaken, or discrete. I cannot remember, but you can double check on that. Okay, but by the end of the day, the source of your arrival also important. Okay, and then how to move about. So it's not it's not a one size fits all situation. Okay, but if let's say you are able to have a system, and you are able to reflect your system and try to somehow make it works, to be able for you to transform your system into a MM1 or also MMM model, I really really recommend you to do that. Why? Because that one is a very straightforward formulation, and the solution is also straightforward. The difficult part is on the estimation part, where you need to estimate a little bit the waiting cost, and some other relevant information that you think quite difficult for you because if let's say you are lack of experience, for example, it's a little bit difficult on that sense. But if you are able to utilize a little bit of other people's experience and put that into practice, the way to solve that is very easy. You can see over here, right? You only need to know your average of those two problem, your waiting and also your service, and then voila, you put inside your system, and then you click enter, you get the whole information, and then you can tie with your valuation of your cost. Interesting, isn't it? And then you can play around with different alternative that you have in a business area, for example. It's quite interesting for you to play around with these particular models. Okay, so I hope you enjoy the lesson, especially on the probabilistic part one for queuing model. And later we are trying to look at another probabilistic model. Okay, sorry, part two. Another, we are going to look at another probabilistic model, in particular Markov chain, and we see how it goes. Okay, so um, all the best with your understanding of mathematical modeling. So I'll see you guys in the next lesson.